You're trying to calculate the acceleration of gravity on another planet, but remember, the idea here is that this is the only force acting on you. We're trying to see how much you would accelerate if we dropped you near the surface. So net force equals ma. The idea is this is the mass of you, or anything. We're going to be canceling this out. But I was surprised to see people using their mass still. That's not necessary. Remember, the other side of this is the mass of the planet, the mass of the object, g, over r squared. That has to equal the mass of the object times a. We are dropping something near the surface of the planet. So we actually don't need the mass of the object to do this. I mean, it's nice that you put yourself in there again. But remember, we could be dropping anything. A house, a bike, you. It doesn't really matter. We're just trying to find out what the acceleration would be. That just leaves us with stuff about the planet. The mass of the planet, g, and the radius of the planet squared. Now, even still, you got to put the stuff in there correctly and push the buttons right, and don't forget to square it, all that kind of stuff. It's got to be a reasonable number. We've sent stuff there. I mean, so if you got like 1,000, those things would be crushed. That's an acceleration so great that when they finally got close to the ground, it would just crush them to death. There'd be nothing there. So it has to be something reasonable. It's going to be more than the moon. So try again if you haven't tried already, and figure it out. It's not hard. I mean, you can look it up. So you can check your work. You have, the little internet with you. Some of you have the medium-sized internet. But this is the answer. Now, let me hold on to you guys. We have lots to do today. This is just a part of it. Just want to see if you paid attention yesterday, because this is what we did yesterday. We have a lot more we're going to do today. But let's take a look at another example of this, just so you guys can kind of practice, because there's over here. There's a more likely way you'll be faced with something like this. All right, so hear me out. This is what it would sound like. Hear me out. I don't want you to use the actual mass of the Earth. I don't want you to use the radius of the Earth to do this. Because they could just make this, a planet has an acceleration of gravity of 12 and then do this again. And you don't need the mass of the Earth or the radius of the Earth to do this. So this is kind of an SAT style question. There's some reasoning to be done here. And if you understand how to do these, then go off and do it. It's not so hard. If you don't understand how to do these, I can give you several different methods. But I'm going to go with kind of a straightforward method. To do a problem like this, you have to already have an understanding of what it is you're calculating. So for us, we're calculating the acceleration of gravity. So we have to already know that's mass of planet g over radius of planet squared. We have to start with a relationship. And this is the relationship we're starting with. It's the same thing we just had. Now, they gave us a starting place. They said we're taking this new planet and comparing it to the Earth. So I'm going to transform this to talk about the Earth. Mass of the Earth, g over radius of the Earth squared. Okay? Here's the method I would have you do. You'll notice they gave us comparisons to values about the Earth. Do you see that? So what I want you to do is put in their changes. For example, they said it's 2 times the mass of the Earth. And they said it was half of the radius of the Earth. So wherever there was mass of the Earth, I'm putting in the change. And wherever there was radius of the Earth, I'm putting in the change. This is the method. So for you guys who are just hastily copying down the stuff and will have nothing in your notes besides what I'm writing on the board, take a minute. Write down what you had to do to go from here to here. You had to take each of the changes that were in the problem and apply them to the variables. Write yourself instructions here. I won't go over this again after this. This shows up frequently, but not often enough where I want to do a bunch of stuff. You'll have homework on it. Now next, pull the numbers to the left and push the constants to the right. So I'm gonna separate the 2 and leave ME times G to the right. And I'm gonna separate out the 1/2 squared and push the RE squared to the right. So I'm separating the numbers from the constants. Now, over here I have MEG over RE squared. I pulled that out. Here I have 2 divided by 1/4, which by the way is 8. This is 8, this is G, right? Because that's what we started with. By pulling the constants out, we get back the original value. And by pulling the numbers out, we get a scalar. These problems will often have, by how many times does this planet's gravity of the Earth's gravity, or something like that. And they'll have numbers like 1/2, 1/4, 8. It'll be something where you'll have multiples of how the 2 and the 1/2 could be put together. These are super common problems. And it doesn't have to be about gravity. They can do this in any equation that's been given to you. They do this with the gravity equation specifically because it's got the r squared in the denominator, and there's things about it that they can change. So they do this all the time. We're going to practice another one just to make sure we're all kind of paying attention. So did you figure out that this was the force of gravity equation that we're working with? And that our first instance of this is that it equals 2. And they tell us that we're going to have half the mass of one of the objects, but we're going to double the separation distance. So pull the numbers out to the left and the constant's out to the right. Recognize that this is the original size of the force. And I have 1/2 divided by 4. These are always going to have stuff like answer A, B, C, and D. And they're going to be the obvious things like 4 newtons, 2 newtons, 1/2 newton, 1/4 newton. And they're going to see if you're making mistakes, because one of these is what happens if you don't square the denominator. One of these, if you don't understand how to deal with the fractions, they're going to have those kinds of answers. These are super common on the exam. They're garbage. They have nothing to do with physics, but they have them on the exam all the time. And they can pick any equation. It's not about the equation. They pick this one often because of the r squared in the denominator, and people forget that kind of stuff. But this is pretty typical stuff on the exam. So in the example that we just saw, let me see if I can kind of draw this for us. I've got my little tube at the center. There's a stopper out here someplace. So there's my stopper, and I had a piece of string attached to it. If we freeze a moment in time, like this moment, us looking down on the stopper, watching it spin in a circle, and we consider just looking at this moment in time, the stopper had a velocity at this moment in this direction. We would call this the tangential velocity. Meaning at that instant, because velocity has to have direction, that had to be the direction of the velocity at that moment. But the string was pulling on the stopper. It pulled on the stopper in this direction. This had to be the direction of the tension, which just by geometry, this has to be a right angle. Everybody following along so far? Pretty straightforward. Newton's second law. If there is an unbalanced force, our object has to accelerate. The tension is an unbalanced force. So the object had to accelerate. But this object didn't speed up or slow down. That's the whole point of this. And that's why I asked you guys, am I swinging it at a nice constant speed? I tried to make sure that I was. So it wasn't getting faster or getting slower, it was changing direction all the time. Well, so far this year, whenever we've talked about accelerations, they've always been about how much the speed changes. This is a case where the object's speed never changed. And we talked about this a couple weeks ago when I drew the winding road. We talked about the object traveling along that winding road. So here we have the specific case where an object has an acceleration that is just about its direction changing. We have a name for this, and we call this a centripetal acceleration. Yeah, this is the case where the object's speed is not changing, but its direction is changing. This is a special kind of acceleration called a centripetal acceleration. In order to have a centripetal acceleration, several things have to happen. First, you guys still writing the last thing? Just write faster. In order to have a centripetal acceleration, several things have to happen. First, your unbalanced force has to be perpendicular to your velocity. I'm saying this because if the unbalanced force has a component in the direction of the velocity, then the object's speed will change. Like if I pulled on it with this tension instead of the other tension, part of this tension would be this way and would cause the object to speed up. Part of the tension would be this way too, which would cause it to change direction. But if I only wanted the object to change direction, I would want to make sure there was no part of the tension in the direction of motion. That's what makes this special. This is a very special case where the object's direction is the only thing that's changing. Speed is staying the same. But the only way I can do that is to have an unbalanced force that is perpendicular to the velocity. Now hear me out. That means this object has only a very narrow way that it can move. If we consider what happens a few seconds later, maybe not even seconds, but milliseconds, the object will have moved to here. And the only way that it could continue to do so is if the tension also changed direction to stay perpendicular to the velocity. In the case of the stopper and the string, that meant that the string always had to pull towards the center of the circle. That's why this is called a centripetal acceleration. The root of this word is center, and petal means seeking or looking. Centripetal accelerations are accelerations that point towards the center of the object's motion, what we call the radius of curvature. Centripetal accelerations are accelerations that are pointed along the radius of curvature, the center of the object's motion. We say radius of curvature because this doesn't have to just apply to an object traveling in a circle. Anytime any object changes direction, its change in direction will have a radius of curvature. If it's a car making a left, if it's Lance running in a circle, any one of these will require an object to have some form of a force pointed along the radius of curvature. It has to happen every time you change direction. So anytime an object goes from traveling one direction to another, there will be a pathway that has a radius of curvature and a force directed towards the center of that path. Now, centripetal accelerations. To calculate a centripetal acceleration, we can't talk about the change in velocity over time. So there is another way to calculate centripetal acceleration. Since the velocity is staying the same, it involves how fast you're going and the radius. And I think these things make perfect sense as to why they're there. If you're traveling faster, it takes more acceleration to turn you. Well, that's why it's in the numerator, and it's squared. So pay attention to that. Small changes in velocity require big changes in acceleration. You know, if the sign says to make that turn at 15 miles an hour, and you make it at 30 miles an hour, well, it's going to take 4 times the amount of force for you to make that turn. So understand that small changes in velocity deliver huge changes in acceleration. Also, if I want to make the turn tighter, meaning turn with a smaller radius, well, then I'm going to need more acceleration, more force. This is why all of you guys are hard to drive around, because you don't understand these principles, and a lot of parents aren't either. Make the turn from, say, Gun Highway to Citrus Park Boulevard. You guys know where I'm talking about? It's a rough turn because it's not 90 degrees. It's about 110 degrees. So you have to turn more than just a right angle. You're supposed to go from the leftmost lane to the leftmost lane. That's how you're supposed to make any turn. Now that there's 2 turn lanes, that's confused people. And you'll see them drifting out of their left lane and into that middle lane. They're not supposed to, but they do it all the time. And what's worse is the people coming in from the other direction who are making a right turn. They're supposed to turn from the rightmost lane to the rightmost lane. That's the tightest version of the turn. If you're going too fast, though, you tend to have to make your radius bigger to compensate, or else you feel like your car's losing control. You have a limit to how much acceleration you have. Be a passenger. and sit on that passenger side. And when somebody makes the turn right there at Citrus Park Boulevard, look at the opposite corner and see how blackened it is from all the people who have not made the turn successfully and have slid into the corner. And watch how many times, or look at all the dents that are in the light pole that's right there from all the cars that have wrapped themselves around that light pole. It happens about once a week. Somebody slides off the road into that corner. It's pretty crazy, but happens all the time. The thing is, the only way to make this kind of turn is you must have some kind of unbalanced force causing you to make this turn. There are no centripetal forces. I'm not adding a list of forces to your list that you have. There must be an unbalanced force, something out of your list already, that causes an object to travel in a circular path. For the stopper, it was tension. In fact, I would say that tension equals mv squared over r for the stopper. This is just the case of the stopper, but that was the unbalanced force, and the stopper was clearly traveling in a circular path. There had to be some external force to cause the object to travel with a centripetal acceleration. Now just be aware, you can have both. You can be speeding up and turning at the same time. You guys, I see it all the time. You want to make that light, the light's turning yellow, so you speed up. You get into the intersection, realize you might be going a little faster than you anticipated. So what do? You jerk the wheel to the left and you slam on the brakes. You are slowing your car down and turning at the same time. That means there's a component of acceleration that is tangential to your path, a tangential acceleration, and there's a component of your acceleration that is radial to your path. And combined, it causes you to turn and change direction, turn and change your speed at the same time. You can do both. We're gonna focus on situations where only one of these things is happening, because that's probably enough for you guys. And we'll get good at that, and then when we've gotten good at that, we'll add both at the same time. How many of you know what one of these is? Let's see if I can draw this correctly. Kind of looks like that. I'll draw it from the top and I'll draw it from the side. Somebody told me that there's still a few of these around, but my experience is that there's not. Did you say stop sign? Just stop. Your silly little grin back there is enough for me to understand that there's limits.
It's a clock.
It's not a sand dollar. This is from the top. Let's see, from the side it would look like this.
Oh, is that the playground?
Oh, yeah.
There. It's hard to find these anymore, isn't it? And because, and it's not too much of a secret as to why. It's because little kids get their head stuck down there and it's game over and we can't play anymore because some stupid parent didn't watch their kid, and so now all the fun is gone for everybody. But anybody ever get a chance to play on one of these? I mean, the parents that are just ruining parks for everybody else. How many of you have seen one of these? Let's see. They always got some weird shaped thing.
The springy orange.
Yeah. Right. So when I was going to the park a couple months ago with my niece, they had replaced all the springs with posts.
No!
Like,
How does that work? You just sit there and...
you just sit there. It's like we don't have anything else to put here, so here we go. Hop on, kids, and have fun. It's terrible. You know, it's hard to find a park with a spinny thing like this. They make these little spinny things like where one kid could sit on it and it's kind of at an angle. You've always seen the kid that's trapped on it and can't get himself off because he's going too fast. And these are a blast because you could convince your little brother or sister or somebody to get on there, and then you and your friends would like just spin it around until they flew off, right? Good times, good times. Now there is the adult version of this, or I say adult, let's just say the big person version of this. I'm hoping all of you have ridden. It tends to look like this. That's from the top and from the side. It's one of these. Oh, teacups, no. although teacups are the same kind of idea, where he's got you and your friends are all kind of in here, and the whole thing spins. There's a couple versions of it. There's the one that's all open, and it kind of tilts while it's spinning. You guys know what I'm talking about? You have to go to the fair to see these kinds of things. And then there's the ones that are all inside, and you kind of stick to the wall. A long time ago, they used to have this in Busch Gardens too. Busch Gardens had one of these. They've had two different versions over the years. They don't have any right now. But over by where the bumper cars were, on the other side of that used to be 3 rides. One of them was like a teacup ride, but one of them used to be like this, but it had a really small radius. There's reasons why you design rides this way. The human body doesn't experience velocity, it experiences acceleration. So we tend to be more excited around rides that have accelerations. Going fast is not necessary generally because your body can't feel velocity. When you go in an airplane, you're doing 600 miles an hour, you really have no idea you're going 600 miles an hour. Everything is small on the ground. In fact, the slowest time, I talked about this, the slowest time you're on an airplane is takeoff and landing. The rest of it's when you're really moving. All a roller coaster has to do is make you go slow, but go close to things. So most of the roller coasters that you've ever ridden are never any more than about 30 miles an hour. They don't have to be. They can get you really close to obstacles, and that's their goal, to make them appear faster than they are. But what the body can feel is acceleration. You have very sensitive acceleration detectors in your ears and in other more southerly places. And those places tend to feel accelerations. And because of that, the whole butterflies in your stomach thing, it's not your stomach. So my point is, what force causes you to go in a circle here? There's no centripetal force. It's the first thing I said. There's a centripetal acceleration because I'm pretty sure this guy is traveling this way, and then after a few moments, they'll be over here traveling this way, right? If the ride is spinning like that, they're going to go from here to here. What causes them to do so? It's not a new force. It's got to be something from your list. What are they in contact with?
Oh, the wall.
The wall. It's a normal force, yeah. In these rides, it's a normal force that causes them to travel in a circle. What you have to understand is that for any object traveling in a circle, there will be an unbalanced force. This force is going to come from your list. It can be tension, if we're talking about the stopper on the string. Normal force, if you're standing against a wall and the wall is spinning. Friction on your tires, if your car is making a turn. These are the forces that cause things to travel in a circle. In fact, I would have written all of those things down. Or else, when we do homework next, you're going to raise your hand and ask me a silly question about, what do you mean friction? Yeah, it's friction that causes you to make a turn. That's what it is. That's the only force that can act on the tires. That's horizontal. And same with your shoes when you make a turn when you're walking down the hallway. It's still going to have to be friction acting on your shoes. It's going to be from your list of forces. There are no centripetal forces. There are forces that cause centripetal acceleration. Understand, that's a very different statement. There are no centripetal forces. There are forces that cause centripetal acceleration. A centripetal acceleration is any acceleration that causes you to change direction, which is why we talk about orbits and circular motion at the same time. In fact, the first thing I want to talk about are objects that travel in low Earth orbit. Consider something small, like the Dragon capsule that meets with the International Space Station. I'm just going to draw a little dot here. The International Space Station is in a relatively low Earth orbit. And when I say relatively low, let me just remind you that the radius of the Earth is really big. 6.37 times 10 to the 6th meters. So technically that would be the distance from here to here. That would be the radius of the Earth. The problem is that altitudes above that, that's the distance from the surface of a planet to where you might orbit. We call that the altitude. I said that would be a definition later. If you're given an altitude, that's probably not the orbital radius. The orbital radius will be the distance from the center of the planet to where your object orbits. That's an orbital radius. That works for most cases if you're far enough away from the planet to make a difference. Things like the International Space Station and where the space shuttle used to fly, that's just above the atmosphere. That's not enough to even change this number when you add it to the radius of the Earth. So what we're going to do is calculate a orbit for something that's in low Earth orbit. And basically what we're saying is that the object is just very near the surface of the Earth. We'll be off by a couple of seconds, but here's how we calculate orbits. First, to calculate an orbit, you have to understand that this is still an object traveling in a circular path. It has some kind of tangential velocity. In order to be in an orbit, you have to give an object the right balance of velocity, radius, and force. In this case, the net force acting on the object is causing it to travel in a circle. So today we're talking about a subclass of orbits, circular orbits. Tomorrow we'll talk about generic orbits that are elliptical. Most orbits are elliptical to some extent, but we're going to just talk about circular because that's within our capability of calculating. The first thing I want you to realize is that the unbalanced force is the force coming from gravity. It's going to deal with the mass of the planet and the mass of the object that's orbiting. And we're going to make a couple of assumptions for the time being. First, we're going to assume that the mass of the planet is much bigger than the mass of the object that's orbiting. That's kind of important. If these two things are nearly the same mass or are of similar size, then one doesn't actually orbit the other. They orbit around their center of mass. So that becomes a more complicated problem. The Earth and Moon are like that. This is why the Earth wiggles on its orbit, because the Moon is big enough for them to orbit around their center of mass, not the center of the Earth. But like the Earth and Sun, the Earth is not big enough for that. The Earth is the object, and the Sun is at the center, and we orbit around the Sun's center. It's because the mass of the Sun is like 10 to the 30th kilograms, while the mass of the Earth is just 10 to the 24th kilograms. Anyways, this is going to be the force of gravity. So on our net force side, we're going to be using that. But I want to be really careful. You use the radius of the planet when you can, but it has to really be the orbital radius. So if you're anything but right at the surface, you'll have to add the altitude to that. So like we would need to find the distance between the Earth and Sun if we wanted to calculate the orbital properties of the Earth and Sun. This side, this object is the object that's doing the orbiting. In this case, the Dragon capsule, the International Space Station. And it has to be a centripetal velocity. So that's going to have to be our v squared over r, where r is the radius of curvature. That is also our orbital radius. You do need to ask yourself if the separation distance is also the orbital radius. It's important to do so. All of our problems are going to be like this for the time being, but that may not be true next semester when we start looking at more interesting things. But for right now, we're going to treat them together. Now, I've given you all the things that I want you to have, but I want you to figure out how fast the Dragon capsule has to be traveling to be in low Earth orbit. You have all the things necessary to do so. I've given you the mass of the Earth and the radius of the Earth. You don't actually need the mass of the capsule. If you look closely here, you'll notice that whatever's orbiting, their mass cancels out. Now, my expectation is that you're going to come to school tomorrow with this information done. I'm going to tell you that the velocity is over 7,000 meters per second. That's how you know you're doing it right. And I expect you to come tomorrow with that information. And one more thing. I want you to tell me how long it takes an object to orbit the Earth near the surface. we've used this relationship before. I want you to use it again.